In the first video, I told you about formal proofs, and I showed you one of the proof rules that are used for building proofs, and I showed you a couple of examples of proofs that use that rule. In this video, I'm going to tell you some more of the rules that we use for building proofs. There are two sorts of proof rules in our system, which are called introduction rules and elimination rules. Each of them is associated to one of the logical connectives that we use for building formulas. So for each logical connective, we have an introduction rule and we have an elimination rule. The idea of an introduction rule is that it says, if we want to prove a formula with this connective in it, how do we do it? And an elimination rule says, if we've already got a proof of something with that connective in it, what can you do with it? So together, between the introduction and elimination rules, we have a sort of back and forth between what you want to prove and what you've already proved. The first connective we'll look at is implies. The introduction rule for implies is the one we already saw in the last video. Let me write it again. So it says, if we want to prove P implies Q, then we need to prove Q from the hypothesis P. Now, if you remember last week, we had an annoying thing where we had a whole extra list of unused hypotheses which were repeated both above and below the line. This turns out to be really annoying when you're actually writing proofs. So we're going to use a convention that you only need to write each hypothesis once, and then it's implicitly going to be copied everywhere above. So the implies introduction rule is now going to be written like this, and it has this name, implies I. So let's talk a bit about what this proof rule actually means. So I can make instances of this proof rule where I substitute any formulas for P and Q. So you can use this proof rule anytime you want to prove a formula that has the form something implies something. So you saw examples of this last week when I was writing proofs. And then so when you want to prove something implies something, you substitute these two somethings for P and Q in this rule. Okay, the next rule is implies elimination. So the question is, if you already know that P implies Q, what can you do with that knowledge? Well, if you know that P implies Q, and you also know that P, then you can deduce that Q. So the implies elimination rule looks like this. If you know P implies Q, and you know P, then you know Q. So this is an example of a proof rule that has two different things above the line that we need in order to build a proof of Q. So we can build a proof of Q if we have a proof of P implies Q and we also have a proof of P. So what this means is that proofs that we write start to look a little bit like trees because it branches into two parts when we use a rule like this. Elimination rules are going to be named for short, like, and I haven't left myself enough space, implies E for implies elimination. Okay, the next connective we're going to look at is and. And after we've looked at and, then I'm going to show you some more examples, because if I gave you all the rules at once, it would be too much information for one video. For the and introduction rule, we need to think, how do we prove something of the form P and Q? Well, to prove P and Q, we need to prove P, and then also separately, we need to prove Q. So we know P and Q if we know P and we know Q. So if we have a proof of P and we have a proof of Q, we can join them together to make a proof of P and Q. This is and I for introduction. So this is another example of a branching proof rule. Now for the elimination rule for and, what can we do if we know that P and Q? Well, one thing that we know is that P, so we could forget that we also know Q. Or alternatively, we could deduce that Q and forget that we know P. So there's actually two different elimination rules for and. one that allows us to deduce P and one that allows us to deduce Q. So one of them looks like, if we know P and Q, then we know P. And the other one says, if we know P and Q, then we know Q. And I'm going to give these two rules different names. One of them is and elimination left, and one of them is and elimination right. Okay, there's one more rule that we need before we can actually build any proofs, and that's the stopping rule. So before we said you can deduce the conclusion immediately when it's the same as one of the hypotheses on the left-hand side of the turnstile. But today we have a new convention, which is that we only have to write a hypothesis once, and then implicitly it's copied everywhere above it. So now we need to modify our stopping rule a bit to account for that. So now the stopping rule is going to say we can deduce the conclusion if it's the same as a hypothesis that appears on the left of the turnstile, either right there where you're using the stopping rule, or anywhere lower down. And by lower down, I mean lower in the branching tree-like structure. If it's physically lower on the page, but it's on a parallel branch, and we can't reach it without turning around and going upwards, then we're not allowed to use it. It has to be somewhere in the proof that you can reach just by going down the branching structure. We will see some examples of this. Okay, that's enough proof rules for today. For the rest of the video, I'm going to show you a couple of examples. These are going to be formulas that involve both and implies. So our first example is A and B implies A. So for now, we'll use brackets, and then later I'm going to introduce some precedence rules so that we don't need so many brackets. How do we prove this? Well, this has the form something implies something, so we can apply the implies introduction rule. So by using implies introduction, we need to prove A from the hypothesis A and B. You might have noticed a pattern by now, which is everything that I've proved so far has the form something implies something. That's not really a coincidence. In the majority of examples, we're going to start by using an implies introduction. Okay, so now we need to prove A from the hypothesis A and B. So what can we do here? So I have some general bad news for you, which is that writing proofs is not really something that you can do mechanically. There's not really an algorithm you can apply or a handle that you can turn. Writing proofs is something that takes experience, and sometimes it takes some creativity. So what can we do here? Well, one thing that we can do is we can apply and elimination, because to prove A, it is enough to prove A and B by the and elimination left rule. And now we're done. So now we can apply the stopping rule, because our conclusion A and B appears on the left-hand side of a turnstile, namely here. So I can write a line above, and now we're done. Okay, here's an example that's a little bit more complicated. The thing that we want to prove is A and B implies B and A. Okay, so as usual, we need to start by using implies introduction. So we need to prove B and A from the hypothesis A and B. Okay, so now we need to prove something that has the form something, and that's what the and introduction rule is used for. So we apply and introduction, and now the proof branches. we need to prove B, and we also need to prove A. Okay, so let's focus on each of these branches separately. In the first branch, we need to prove B. This is kind of like the previous example. So in order to prove B, we're going to use and elimination, this time on the right. So to prove B, it is enough to prove A and B. And now we can apply the stopping rule because we have A and B on the left side of the turnstile further down, namely here. So I can write a line above, and now we're done with that branch. But we're not done overruled because we have another branch which is unfinished. So on the other branch, we need to prove A. And this time we're going to apply and elimination on the left. And now we need to prove also A and B. And again, we're also done because we still have A and B on the left of the turnstile further down. So I'm going to write a line to say we're finished with this branch. And now we're finished overall. So that's a complete proof. Okay, that's enough for this video. In the next video, I'm going to show you the software that Connor has cooked up, which is called Ask. This is a computer implementation of this formal system, and that's what you're going to be using to do all of the exercises on this.